The gem box should not contain more than 6 conductors entering or leaving. With 314/2 cables, there are already 6 conductors plus the ground wire. Adding a larger gem box will alleviate this violation. It is not good practice to tap off receptacles for lighting. This practice can lead to overloading and potential fire hazards. According to the National Electrical Code, separate circuits should be used for lighting and receptacles. Mixing these loads on a single circuit can lead to overloading and nuisance tripping of the circuit breaker. The bedroom should have ground fault circuit interrupter protection for all receptacles within the bathroom and any outdoor receptacles. Additionally, arc fault circuit interrupter protection is required for all outlets and bedrooms. Install a larger gem box to accommodate the additional conductors. If possible, run a new feeder to install a separate circuit for the lighting in the bedroom. This will ensure that the lighting and receptacles are on separate circuits. Install ground fault circuit interrupter outlets in the bathroom and outdoor areas, and arc fault circuit interrupter outlets in all bedrooms. Remove the tapped-off connection to the floodlight and wire it directly to the switch box. Since the discovered violation is on a single circuit, it is advisable to inspect other circuits in the house for similar violations. Ensure that all electrical work complies with the National Electrical Code and is performed by a qualified electrician. Discuss the recommended changes with the customer and obtain their approval before proceeding. If the cottage is likely to be expanded or modified in the future, consider installing a subpole or additional circuits to accommodate future electrical needs. Considering the overcrowding issue, the National Electrical Code (NEC) specifies requirements for box fill to ensure safe and reliable electrical connections. The NEC Article 314.16 covers conductor fill-in outlet device and junction boxes. Several factors contribute to the box fill calculation. Firstly, the number of conductors. Each conductor that originates, terminates, or passes through the box counts towards the fill calculation. Secondly, conductor size. Conductors of different sizes have different fill requirements. For example, a 14 American wire gauge AUG conductor takes up less space than a 12 American wire gauge AUG conductor. Thirdly, device yokes. Device yokes, such as those for switches and receptacles, also contribute to the box fill calculation. A single yoke counts as 2 conductors based on the largest conductor connected to it. Fourthly, internal cable clamps. Internal cable clamps, if present, count as 1 conductor based on the largest conductor entering the box. Fifthly, equipment grounding conductors. The number of equipment grounding conductors also affects the box fill calculation. The NEC provides tables that specify the maximum number of conductors allowed in standard box sizes. These tables are based on the conductor size and the box volume. For example, NEC Table 314.16 provides the maximum number of conductors allowed in metal boxes, while NEC Table 314.16 B covers non-metallic boxes. To determine the appropriate box size, you must calculate the total fill based on the factors mentioned earlier and then select a box that meets or exceeds that requirement. Using a box that is too small can lead to several problems. Firstly, overheating. Overcrowded boxes can cause conductors to overheat due to restricted airflow. Secondly, insulation damage. Excessive pressure on conductors can damage the insulation, increasing the risk of shorts and ground faults. Thirdly, difficulty in making connections. Overcrowding makes it difficult to properly connect wires and devices, leading to loose connections and potential failures. Fourthly, code violations. Using an undersized box violates the NEC and can result in fines or rejection during inspection. When upsizing the gem box, consider the physical space available and the ease of installation. There are various types of electrical boxes available, each with its own advantages and disadvantages. Firstly, metal boxes. Metal boxes are durable and provide good protection against physical damage. They are commonly used in commercial and industrial applications. Secondly, non-metallic boxes. Non-metallic boxes are lightweight, corrosion-resistant, and easy to install. They are suitable for residential applications. Thirdly, gainable boxes. Cannibal boxes allow multiple boxes to be joined together to accommodate multiple devices or switches. Fourthly, adjustable boxes. Adjustable boxes can be adjusted to accommodate different wall thicknesses. When tapping off a receptacle for lighting, you are essentially creating a branch circuit from an existing circuit. This practice is generally discouraged due to several reasons. Firstly, overloading. Tapping off a receptacle can overload the existing circuit, especially if the lighting load is significant. Secondly, voltage drop. The additional load can cause voltage drop, affecting the performance of both the receptacle and the lighting. Thirdly, safety hazards. Overloaded circuits can create a fire hazard due to overheating of conductors and devices. The NEC specifies requirements for branch circuits, including the maximum number of outlets and the types of loads that can be connected to each circuit. In general, it is recommended to have separate branch circuits for lighting and receptacles to avoid overloading and ensure reliable power distribution. The NEC also specifies requirements for the types of wiring methods that can be used for branch circuits. Common wiring methods include firstly, non-metallic sheath cable, commonly known as Romex, which is suitable for residential applications. Secondly, electrical metallic tubing M, which is a thin-walled steel conduit. Thirdly, rigid metal conduit RMC, which is a heavy-walled steel conduit used in harsh environments. Fourthly, flexible metal conduit FMC, which is a flexible conduit used for short runs to connect devices or equipment. Single circuits for lighting and receptacles can lead to several problems. Firstly, overloading. Mixing lighting and receptacle loads on a single circuit can easily overload the circuit, especially if there are multiple high-wattage appliances connected to the receptacles. Secondly, nuisance tripping. Overloads can cause the circuit breaker to trip frequently, disrupting power to both the lighting and the receptacles. Thirdly, difficulty in troubleshooting. When a circuit trips, it can be difficult to determine whether the problem is with the lighting or the receptacles. The NEC recommends separate circuits for lighting and receptacles to provide better load management and prevent overloading. The NEC specifies the maximum number of outlets allowed on a single branch circuit. For example, a 15 amp circuit is typically limited to 10 to 12 outlets, while a 20 amp circuit can have up to 13 outlets. These limits are based on the assumption that each outlet will draw a certain amount of current. Ground fault circuit interrupters and arc fault circuit interrupters provide different types of protection against electrical hazards. Ground fault circuit interrupters protect against ground faults, which occur when current leaks from a circuit to ground. This can happen if a person comes into contact with a live wire and a grounded object. Ground fault circuit interrupters work by monitoring the current flowing into and out of a circuit. If there is a difference of more than a few milliamperes, the ground fault circuit interrupter will trip, cutting off power to the circuit. Arc fault circuit interrupters protect against arc faults, which are dangerous electrical discharges that can cause fires. Arc faults can occur due to damaged insulation, loose connections, or faulty appliances. Arc fault circuit interrupters work by detecting the unique characteristics of arc faults, such as high frequency noise and erratic current flow. When an arc fault is detected, the arc fault circuit interrupter will trip, cutting off power to the circuit. The NEC requires ground fault circuit interrupter protection in several locations, including firstly, bathrooms. All receptacles in bathrooms must be ground fault circuit interrupter protected. Secondly, outdoor areas. All outdoor receptacles must be ground fault circuit interrupter protected. Thirdly, kitchens. Receptacles serving countertop surfaces in kitchens must be ground fault circuit interrupter protected. Fourthly, unfinished basements. All receptacles in unfinished basements must be ground fault circuit interrupter protected. Fifthly, garages. All receptacles in garages must be ground fault circuit interrupter protected. The NEC requires arc fault circuit interrupter protection in several locations, including firstly, bedrooms. All outlets in bedrooms must be arc fault circuit interrupter protected. Secondly, family rooms. All outlets in family rooms must be arc fault circuit interrupter protected. Thirdly, living rooms. All outlets in living rooms must be arc fault circuit interrupter protected. Fourthly, dining rooms. All outlets in dining rooms must be arc fault circuit interrupter protected. Fifthly, hallways. All outlets in hallways must be arc fault circuit interrupter protected. When installing ground fault circuit interrupter and arc fault circuit interrupter protection, it is important to follow the manufacturer's instructions and the NEC requirements. Firstly, choose the right type of device. Make sure to select a ground fault circuit interrupter or arc fault circuit interrupter that is appropriate for the application. Secondly, install the device correctly. Follow the manufacturer's instructions carefully to ensure that the device is properly installed. Thirdly, test the device regularly. Test the ground fault circuit interrupter and arc fault circuit interrupter monthly to ensure that they are working properly. Separating the lighting circuit involves running a new cable from the electrical panel to the bedroom to create a dedicated circuit for the lighting fixtures. This will isolate the lighting load from the receptacle load, preventing overloading and nuisance tripping. Before starting the installation, turn off the main breaker to de-energize the electrical panel. This will prevent electric shock. Secondly, identify a spare breaker slot in the electrical panel. If there is no spare slot, you may need to install a sub-panel. Thirdly, run a new 14/2 cable from the electrical panel to the bedroom. Follow the NEC requirements for cable routing and support. Fourthly, connect the black wire to the breaker, the white wire to the neutral bus, and the green or bare wire to the ground bus in the electrical panel. Fifthly, in the bedroom, connect the black wire to the hot terminal of the lighting fixtures, the white wire to the neutral terminal, and the green or bare wire to the ground terminal. Sixthly, turn on the breaker and test the lighting circuit. Ensure that the lighting fixtures are working properly and that there are no shorts or ground faults. Rewiring the switch leg involves disconnecting the existing wiring and connecting the floodlight directly to the switch box. This will eliminate the tapped-off connection to the floodlight and ensure that it is properly controlled by the switch. Firstly, turn off the breaker to de-energize the circuit. Secondly, disconnect the wires from the receptacle that are currently feeding the floodlight. Thirdly, run a new 14/2 cable from the switch box to the floodlight. Fourthly, connect the black wire from the switch to the black wire of the floodlight. Fifthly, connect the white wire from the neutral bus to the white wire of the floodlight. Sixthly, connect the green or bare wire to the ground terminal of the floodlight. Seventhly, turn on the breaker and test the floodlight. Ensure that the floodlight is working properly and that it is controlled by the switch. Inspecting other circuits involves checking the wiring, devices, and connections in other circuits in the house for similar violations. This can help identify potential hazards and prevent future problems. Firstly, turn off the breaker to de-energize the circuit. Secondly, check the wiring for damage such as frayed insulation, loose connections, or improper splices. Thirdly, inspect the devices such as receptacles, switches, and lighting fixtures for signs of wear, damage, or overheating. Fourthly, check the connections in junction boxes and electrical panels for loose connections or corrosion. Fifthly, use a multimeter to test the voltage and current in the circuits. Ensure that the voltage is within the acceptable range and that the current is not exceeding the circuit breaker rating. Sixthly, look for signs of overloading, such as melted insulation, burned contacts, or tripped circuit breakers. If any violations or hazards are found, take immediate action to correct them. This may involve replacing damaged wiring, devices, or connections, or adding additional circuits to reduce overloading. Ensuring safety during electrical work is crucial to prevent accidents and injuries. Firstly, always turn off the power before working on electrical circuits. Secondly, use insulated tools and equipment. Thirdly, wear safety glasses and gloves. Fourthly, never work on live circuits. Fifthly, follow the NEC requirements for wiring and installation. Sixthly, test the circuits after completing the work to ensure that they are working properly. Obtaining customer approval is important before proceeding with any electrical work. This will ensure that the customer is aware of the recommended changes and that they agree with the proposed solutions. Firstly, explain the potential violations and hazards to the customer. Secondly, discuss the recommended changes and their benefits. Thirdly, provide a written estimate of the cost of the work. Fourthly, obtain the customer's signature on a contract or agreement. Considering future expansion is important when planning electrical work. This will ensure that the electrical system is adequate for future needs. Firstly, assess the potential for future expansion or modification. Secondly, consider installing a subhull or additional circuits to accommodate future electrical loads. Thirdly, use larger conductors and conduits to allow for future upgrades. Fourthly, document the electrical system and keep a record of all changes and upgrades. The NEC provides detailed requirements for electrical installations, including wiring methods, conductor sizes, overcurrent protection, and grounding. Compliance with the NEC is essential to ensure the safety and reliability of the electrical system. The NEC is updated every 3 years to reflect changes in technology and best practices. It is important to stay up to date with the latest edition of the NEC to ensure that all electrical work complies with the current standards. The local electrical codes may have additional requirements that are not covered by the NEC. It is important to check with the local authorities to ensure that all electrical work complies with the local codes. The installation of a subpanel can provide additional capacity for future electrical needs. A subpanel is a smaller electrical panel that is fed from the main electrical panel. It can be used to provide power to a specific area of the house or to a specific type of load. Firstly, determine the size of the subpanel based on the expected load. Secondly, select a location for the subpanel that is easily accessible and that meets the NEC requirements for clearance. Thirdly, run a feeder cable from the main electrical panel to the subpanel. Fourthly, connect the feeder cable to the main breaker in the subpanel. Fifthly, install branch circuit breakers in the subpanel to provide power to the individual circuits. Adding additional circuits can also provide additional capacity for future electrical needs. This involves running new cables from the electrical panel to the areas where additional power is needed. Firstly, determine the number and size of the additional circuits needed. Secondly, select a location for the new outlets and devices. Thirdly, run new cables from the electrical panel to the new outlets and devices. Fourthly, connect the new cables to the circuit breakers in the electrical panel. Using larger conductors and conduits can allow for future upgrades. This involves using conductors and conduits that are larger than the minimum size required by the NEC. Firstly, select conductors and conduits that are sized for the expected future load. Secondly, install the conductors and conduits in a way that allows for easy access and modification. Thirdly, document the conductor and conduit sizes in the electrical system documentation. Documenting the electrical system is important for future reference and troubleshooting. This involves creating a detailed record of the electrical system, including wiring diagrams, circuit schedules, and equipment specifications. Firstly, create a wiring diagram that shows the layout of the electrical circuits. Secondly, create a circuit schedule that lists the circuits and the loads that they serve. Thirdly, keep a record of the equipment specifications, such as the voltage, current, and power ratings. Fourthly, store the documentation in a safe and accessible location. Using a multimeter to test circuits can help identify potential problems and ensure that the circuits are working properly. A multimeter is a versatile instrument that can measure voltage, current, and resistance. Firstly, set the multimeter to the appropriate setting for the measurement you want to make. Secondly, connect the multimeter leads to the circuit or device you want to test. Thirdly, read the measurement on the multimeter display. The NEC Table 310.15 B16 provides ampacity ratings for conductors based on their size and insulation type. This table is used to determine the appropriate conductor size for a given load. The ampacity of a conductor is the maximum amount of current that it can safely carry without overheating. The NEC specifies requirements for overcurrent protection to protect conductors and equipment from damage due to overloads and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to trip and interrupt the flow of current when it exceeds a certain level. The NEC requires that overcurrent protection devices be sized to protect the conductors that they serve. The size of the overcurrent protection device is determined by the ampacity of the conductor. Grounding is an essential safety measure that helps to protect people from electric shock. Grounding provides a low resistance path for fault current to flow back to the source, causing the overcurrent protection device to trip and interrupt the flow of current. The NEC specifies requirements for grounding electrodes, grounding conductors, and equipment grounding.